Equipment maintenance and reliability. In the semiconductor industry, equipment maintenance and reliability are essential for achieving high-performance manufacturing. As production technology becomes more advanced, the margin for downtime or equipment failure narrows significantly. Maintenance strategies are critical to minimizing unplanned outages and maximizing tool uptime. These strategies include preventive, predictive, and condition-based approaches, all aimed at preserving the functionality and lifespan of sophisticated semiconductor equipment. Reliability management ensures that systems perform consistently under defined conditions, reducing variability and process excursions. This involves tracking performance metrics, conducting root cause analysis, and implementing corrective actions. Lastly, performance optimization focuses on continuously improving tool throughput, yield, and efficiency. By integrating all three elements, maintenance strategies, reliability management, and performance optimization, manufacturers can ensure smooth, cost-effective operations. This holistic approach to maintenance and reliability supports sustained innovation and competitive advantage in semiconductor manufacturing. Why maintenance matters. Maintenance is not just a support function, it is essential to business success in the semiconductor industry. Equipment costs alone highlight the stakes. A single advanced fabrication tool can cost over $10 million. These tools represent significant capital investments, and maximizing their productivity is vital for achieving a return on that investment. When a tool goes down, the cost of lost production is staggering, upwards of $50,000 per hour in downtime costs. These expenses accumulate rapidly, especially in high-volume fabs operating around the clock. That's why uptime targets are so stringent. The industry standard for required uptime is 99.9%, allowing almost no margin for unplanned interruptions. Achieving this level of performance demands robust maintenance systems, predictive analytics, and proactive management. High reliability ensures continuous production, protects profits, and maintains the competitiveness of the entire manufacturing operation. Why maintenance matters. Maintenance directly impacts both technical performance and business outcomes in semiconductor manufacturing. From a technical perspective, product quality is a top concern. The nanometer scale precision required in today's devices allows zero tolerance for contamination or variation, making reliable equipment essential. Production efficiency is also at stake, as fabs run 24/7, and any unplanned shutdowns disrupt throughput and cost millions. Additionally, safety and environmental standards demand consistent maintenance, especially when hazardous chemicals are involved. Failing to comply with safety regulations can halt operations and lead to legal or financial consequences. On the business side, poor maintenance results in revenue loss due to missed customer deliveries, which can reduce market share. It also risks damaging customer trust, as consistency and quality are expected. Lastly, equipment reliability enables a competitive edge, supporting innovation and technological leadership. Proactive maintenance isn't just smart, it's a strategic investment in long-term success. Maintenance challenges. Semiconductor manufacturing presents an extreme level of complexity when it comes to maintenance. One of the most critical challenges is the high degree of technical complexity. Equipment must operate with nanometer precision, which demands tight control of tolerances, especially in multi-chamber systems. These systems involve intricate automation and use advanced materials, increasing the difficulty of diagnosis and repair. In addition, maintenance is often performed in Class 1 cleanroom environments, which require strict contamination control. This means specialized protocols must be followed, and access to tools is limited, making every maintenance task more challenging. Another major factor is the 24/7 operational schedule. The zero downtime goal puts tremendous pressure on maintenance teams to perform within narrow scheduled windows. There's little room for error or delay. With production always running, Technicians must work efficiently under time constraints and constant production pressure. Together, these factors define why maintenance in this industry is among the most demanding. Maintenance challenges. Maintaining semiconductor equipment requires advanced strategies due to several demanding challenges. First, the high equipment value presents a financial risk. Each tool may cost over $10 million, and replacement parts are also expensive. Compounding this, long lead times for parts can significantly delay repairs and impact production schedules. Next is the issue of workforce readiness. The skilled workforce needed for maintenance must undergo specialized training, often with equipment-specific certification. Unfortunately, the industry faces an ongoing talent shortage, making it difficult to staff teams with the necessary expertise. Without trained personnel, even routine maintenance becomes a risk factor. Lastly, the rapid evolution of technology creates constant pressure. Moore's law drives continual updates in process technology, forcing companies to maintain both cutting-edge and legacy systems. This mix raises the risk of equipment obsolescence. These challenges, financial, operational, and technical, demand highly sophisticated, well-planned maintenance strategies to ensure reliability and competitiveness. Maintenance strategies. Maintenance strategies have evolved significantly, transitioning from basic reactive approaches to advanced intelligent systems. Reactive maintenance, known as fix when broken, is the most basic form. It only addresses issues after failure occurs. Although it has a low initial cost, it leads to high overall costs due to unplanned downtime and production losses. Its effectiveness is only 25%. Preventive maintenance uses scheduled intervals to plan work ahead of time. This reduces equipment failures and allows better scheduling, but often leads to over-maintenance and medium costs, with an effectiveness of 55%. Predictive maintenance is data-driven, relying on sensor monitoring to anticipate failures. With optimal timing and reduced waste, it has low cost impact and 80% effectiveness, though initial setup costs are high. The most advanced is condition-based maintenance using real-time AI. It offers continuous monitoring, machine learning, and self-optimization. This results in minimal costs and 95% effectiveness. Maintenance strategies, adoption and strategic benefits. Maintenance strategies continue to evolve, and their adoption across industry reflects varying levels of technological integration. Currently, preventive maintenance dominates with 45% adoption due to its structured nature and lower complexity. Predictive maintenance follows at 30%, benefiting from increasing use of sensors and data analytics. Reactive maintenance, although less effective, is still used by 15% of industry due to its low upfront cost. Condition-based maintenance, which uses real-time AI, remains the least adopted at 10% due to higher setup complexity and cost. However, the strategic benefits of intelligent maintenance systems are significant. Equipment uptime of over 99.5% is achievable, greatly enhancing productivity. Maintenance costs can be reduced by 25 to 30%, making operations more efficient. Equipment life can be extended by 15 to 20%, reducing capital expenditures. Most importantly, these strategies deliver consistent output, supporting high-quality manufacturing. The future lies in AI-driven autonomous maintenance systems. Reliability concepts. Reliability in equipment performance is driven by key metrics like MTBF, MTTR, availability, and failure analysis. MTBF, or mean time between failures, measures the average time equipment runs before failing. In this case, the MTBF is 2,500 hours. While this is a reasonable figure, the industry target is over 8,560 hours, equivalent to 1 year of continuous uptime. MTTR, or mean time to repair, is 4.2 hours, but the target goal is less than 2 hours. Fast response is critical, with an ideal benchmark of 15-minute response time. The availability formula, MTBF divided by MTBF plus MTTR, times 100, shows the relationship between uptime and repair efficiency. With these values, availability is 99.8%, approaching world-class performance, defined as greater than 99.5%. Finally, failure analysis through root cause investigation helps identify patterns in downtime, allowing for continuous improvement in strategic maintenance planning to maximize uptime and equipment reliability. Reliability concepts, failure timeline, and cost impact. Understanding the typical failure timeline is critical to proactive maintenance planning. Phase 1 represents normal operation, where equipment runs with stable metrics at 100% efficiency. In Phase 2, early warning signs appear. Efficiency drops slightly to 85–95%. If unaddressed, this leads to Phase 3, a critical failure where the system stops abruptly, resulting in 0% efficiency and unplanned downtime. This timeline highlights the need for timely intervention. The financial consequences are significant. On a critical production line, each hour of downtime can cost $45,000. Over the course of a year, if proper maintenance is not performed, the annual loss risk could reach $2.1 million. Cost breakdowns show that 60% stems from production loss, 25% from direct repair costs, and 15% from quality impact. Predictive maintenance offers a strong return on investment, delivering 3x to 5x ROI by preventing failures and minimizing operational disruptions before they escalate. Preventive maintenance. Preventive maintenance is a proactive strategy that focuses on planned, regular upkeep to avoid equipment failure. It operates on 4 key intervals: daily, weekly, monthly, and quarterly. Daily inspections involve 24/7 monitoring tasks like visual checks, temperature monitoring, performance logging, and safety checks, performed every day of the year. Weekly calibrations focus on precision tuning of sensors, power systems, pressure controls, flow rates, optics, and mechanical components, ensuring accuracy 52 weeks a year. Monthly overhauls deliver deep maintenance and include component cleaning, lubrication, and filter replacements. Completion rates for these tasks vary, with cleaning marked complete, lubrication at 75%, and filter replacement at 40%. Quarterly replacements address critical components like RF generators in Q1, pump seals in Q2, gas lines in Q3, and electrodes in Q4. Altogether, this planned schedule covers 85% of maintenance needs, reducing risk of unplanned downtime while maximizing uptime, performance, and the lifespan of critical assets. Preventive maintenance. Preventive maintenance is a proactive equipment care strategy designed to reduce unplanned downtime and improve operational efficiency. One key aspect is planning efficiency, which includes maintaining a high level of schedule adherence, currently at 94%. This means that nearly all maintenance tasks are executed as planned, minimizing disruptions. Resource utilization is also strong at 87%, indicating that manpower and materials are being efficiently allocated. Cost predictability stands at 91%, providing financial stability and allowing for better budgeting. Another benefit of preventive maintenance is the component lifecycle extension, with optimal replacement strategies boosting equipment lifespan by 15 to 20%. This reduces the need for emergency repairs and delays equipment obsolescence. Finally, the ROI impact is significant. With a cost reduction focus, organizations achieve a return rate of 3.2x. Preventive maintenance, when well executed, leads to smarter investments, higher reliability, and long-term cost savings. Preventive maintenance, advanced technologies, and AI-driven analytics. Modern preventive maintenance strategies now integrate advanced technologies with real-time analytics to optimize equipment performance. At the center is the AI engine, which serves as the predictive core. It processes vast data sets from various sources to forecast failures and recommend timely interventions. IoT, or the Internet of Things, connects sensors and devices to stream live operational data, enabling seamless condition monitoring. CM, or condition monitoring, continuously tracks variables like vibration, temperature, and pressure to detect early signs of wear or failure. ML, or machine learning, identifies patterns in historical data to improve predictions over time, while PA, or predictive analytics, uses statistical models to forecast future events based on current trends. With real-time monitoring always active, this integrated system delivers smarter decision-making, enhances reliability, and significantly reduces unexpected downtime. These technologies work together to form a data-driven maintenance ecosystem that is both efficient and responsive. Preventive maintenance, advanced technologies, and AI-driven analytics. Advanced preventive maintenance relies on a tightly integrated system of sensors, analytics, and predictive technologies. IoT sensors play a foundational role by enabling 24/7 data collection. These sensors monitor a wide range of parameters, including temperature, vision, acoustics, current, pressure, vibration, flow, and particle levels, with over 1,000 active sensors deployed. This continuous stream of data feeds into AI and machine learning analytics, which utilize neural networks, deep learning, random forests, and support vector machines to interpret complex patterns. These models achieve a high prediction accuracy of 94.7%. Condition monitoring provides real-time visibility into equipment health, with a 92% accuracy in health assessment, 88% for performance indexing, and 96% in anomaly detection, leading to a 99.2% detection rate overall. Lastly, predictive algorithms process data using active ingestion, engineered features, and trained models. They forecast outcomes with a 72-hour lead time and a rapid 15-minute update rate, ensuring timely and effective maintenance actions. Preventive maintenance, tangible results with AI-driven analytics. Implementing preventive maintenance powered by advanced analytics leads to measurable performance improvements across cost, uptime, and productivity. Cost reduction is one of the most direct benefits, with maintenance costs reduced by 40 to 60%. This is achieved through optimized scheduling, which ensures that interventions are neither premature nor delayed, and by preventing failures before they occur. Downtime prevention is another critical outcome. With the aid of early warning systems and real-time monitoring, up to 85% of unplanned stops can be prevented. This dramatically improves operational continuity and reduces the ripple effects of equipment failure. Finally, efficiency gains are reflected in a 25% boost to overall equipment effectiveness, or OEE. By keeping assets running at optimal performance, reducing time lost to repairs, and ensuring quality output, organizations experience a tangible uplift in productivity. Altogether, these improvements create a strong business case for adopting AI-enhanced preventive maintenance systems. Best practices. Real-world success stories. Real-world implementations of AI-powered preventive maintenance have shown clear, measurable success. In the first case, AI predictive maintenance addressed a challenge of 12% unplanned downtime. The solution involved deploying over 500 IoT sensors in combination with machine learning algorithms to monitor equipment health and predict failures. The result was a significant 85% reduction in downtime, enhancing operational continuity. The second case, a unified platform approach, tackled the issue of siloed data across 15 different fabrication sites. By centralizing IoT analytics into one unified system, companies gained better visibility and control over asset health, leading to a 40% reduction in maintenance costs. The third example highlights robotic monitoring, which replaced manual cleanroom inspections with autonomous AI vision robots. This automation led to a 60% improvement in detection speed, enhancing responsiveness and reducing quality-related delays. Together, these best practices demonstrate an average savings of $2.4 million and follow a clear implementation timeline: assess, plan, deploy, optimize, and scale. Best practices. Adopting best practices is key to achieving operational excellence and long-term value. One foundational practice is making data-driven decisions, which leverages real-time analytics to guide actions and reduce uncertainty. This ensures that strategies are based on factual, up-to-date insights rather than intuition alone. Another critical practice is building cross-functional teams. By integrating talent from various departments, companies gain a holistic view, improve collaboration, and reduce silos, leading to faster, more aligned decisions. Continuous training is also essential. Investing in employee education on the latest technologies ensures that teams stay current and competent in a fast-changing industry. Additionally, iterative improvement through regular optimization helps organizations remain agile, adapt quickly, and steadily boost performance. These combined best practices contribute to a strong ROI, as seen in the 420% return over 24 months and an average break-even period of 12 to 18 months, resulting in significant savings, averaging $2.4 million. Future of maintenance. The future of maintenance is being shaped by emerging technologies tied to Industry 4.0, with a clear evolution projected through 2030. First, digital twins offer a virtual mirror of physical assets, enabling real-time synchronization with 99.9% accuracy and up to a 72-hour lead time in predictive maintenance. Mass adoption is anticipated by 2026, marking a turning point in proactive decision-making. Next, quantum AI dramatically accelerates optimization and pattern analysis, delivering processing speeds up to 10,000 times faster than conventional systems. Though complex, quantum machine learning opens the door to solving previously intractable maintenance challenges, with commercialization expected by 2028. Moving toward full autonomy, autonomous systems will require minimal human oversight, while achieving 99.8% uptime through self-healing capabilities and 24/7 operation. Finally, green AI represents the environmental dimension, cutting energy consumption by 40% and waste by 60%, paving the way for carbon-neutral operations by 2030. These technologies together form a transformative roadmap. Future of maintenance, market, adoption, and skills. By 2030, the maintenance landscape is poised for exponential transformation, driven by advanced technologies and intelligent systems. The global market for AI-driven maintenance is expected to reach $47 billion, underscoring its increasing relevance and widespread application. With a 15% compound annual growth rate, CAGR, and a return on investment of 180%, organizations can expect significant financial and operational benefits. Widespread adoption of AI in maintenance is well underway, with forecasts showing a major shift toward AI-powered systems by the end of the decade. Companies embracing this shift will enjoy predictive capabilities, automation, and efficiency that traditional methods cannot match. To support this evolution, future skills are becoming more critical than ever. Demand for data scientists is projected to grow by 250%, while AI engineers will see a 400% increase. Additionally, digital specialists will be in critical demand to bridge the gap between technology and implementation.